Hello, and welcome to Controllers Tech. In the past, we have interfaced various types of displays with the STM32 microcontroller. These include character LCDs, OLED displays, and several TFT displays, such as the ST7735, IL9341, and others. Today, we will be working with another popular display module that features the GC9A01 controller IC. We'll explore how to interface this display with STM32 using the SPI peripheral. In addition, we'll integrate the LVGL graphics library into our project. And finally, we'll use SquareLine Studio to design a simple test interface. The GC9A01 is typically found in round display formats. This makes it especially suitable for displaying analog or digital clocks, circular data visualizations like pie charts, rounded images and animations, compass graphics, and more. For this demonstration, I'll be using the STM32H562 development board from WeAct Studio. If you're located in India, you can purchase this board directly from shop.controllerstech.com. This particular board features 1 megabyte of flash memory and 640 kilobytes of SRAM, making it an ideal candidate for running the LVGL library efficiently. You can also purchase the GC9A01 based round display from the same website. Alright, let's launch STM32 Cube IDE and begin by creating a new project. As I mentioned earlier, I'm using the STM32H562 RGT6 microcontroller for this setup. Let's assign a name to the project and then click Finish to proceed. Before we begin configuring the system clock, let's take a quick look at the schematic of the development board. As shown here, the board includes an 8 MHz crystal oscillator. Now let's return to the CubeMX configuration view. We will begin with the clock configuration by enabling the external high-speed crystal as our clock source. Since the board includes an 8 MHz crystal, we'll use the PLL phase-locked loop to scale the system clock up to its maximum frequency of 250 MHz. Next, go to the SPI configuration section and enable half-duplex master mode. Because the display only receives data and does not send any data back, a half-duplex configuration is sufficient. You'll notice that pins PA5 and PA7 are assigned as the SPI clock, SCK, and MOSI, master out slave in, pins, respectively. Before we proceed to configure additional pins, let's take a look at the wiring diagram. This diagram shows how the GC9A01 display is connected to the STM32. The display is powered by a 3.3V supply directly from the microcontroller. The clock pin of the display connects to PA5, which is the SPI clock line. The data pin connects to PA7, the MOSI pin for SPI communication. The DC pin on the display distinguishes between command and data signals, and it is connected to PA4 on the MCU. The Chip Select CS pin is used to enable or disable the display module and is wired to PA6. The reset pin of the display is connected to PA3 on the microcontroller. Now that the two SPI pins are already configured, we'll go ahead and set up the remaining control pins. All of these pins should be configured as general-purpose output pins. Also, be sure to rename them appropriately according to their function for better readability in your code. With all pins now configured, let's proceed to adjust the SPI communication parameters. The data size should be set to 8 bits, with the MSB, most significant bit, transmitted first. Before selecting the SPI prescaler value, we'll take a moment to examine the SPI clock source. The SPI peripheral uses the PLL1Q output, so we can reduce the clock frequency by adjusting this factor. I'm setting the factor to 10, which brings the SPI clock down to 50 MHz. Then, I set the SPI prescaler to 4, which further reduces the effective SPI clock to 12.5 MHz. This frequency is suitable for driving the display. The clock polarity is configured to low, and the clock phase is set to the first edge. All remaining settings are left at their default values. You also have the option to enable DMA for SPI transmission. The display driver library supports DMA transfers, which you can activate within the library code. DMA should be configured for transmit-only mode, with the data direction set from memory to peripheral. Set the DMA mode to normal, and the data width should be specified as byte. Additionally, ensure that the DMA interrupt is enabled in the NVC configuration tab. In my case, I will not enable DMA because setting it up on the Cortex-M33 core is a bit more involved. However, you can follow the steps I just outlined if you wish to enable it. That completes the configuration process. Go ahead and click Save to generate the project files now. We will begin by copying the necessary library files required to run the GC9A01 display. Here I have both the GC9A01 source file and the corresponding header file ready for use. You can obtain these files by downloading the complete project package. The download link is provided in the description section of this video, so be sure to check that out. These files are organized into their respective directories. One is meant for the source folder, and the other belongs in the include folder, just as I'll be placing them now. Go ahead and copy the .c file, which is the source code file, into the src directory of your STM32 project. Similarly, copy the .h file, which contains the function declarations and configuration macros, into the inc directory. It's worth noting that these library files are designed to work across any STM32 microcontroller. They are not restricted to this particular development board. That means you can use them in different STM32 projects with minimal adjustments. There is no need to make any modifications to the GC9A01 source file itself. As I mentioned earlier in this video, DMA support has already been integrated into this library. You can clearly see that the DMA-based transmit functions are present in the code. However, these functions are currently wrapped within a use_DMA flag, so they won't be active unless that flag is enabled. Let's move on to the GC9A01 header file. Here, we will need to make a few changes to align the library with the configuration we set up earlier in CubeMX. First, you need to define the correct SPI instance that you're using in your project. If you plan to use DMA for SPI transmission, make sure to set the use_DMA flag to 1 to enable that functionality in the code. Next, you'll define the control pins, CS, DC, and reset, and also specify the GPIO ports to which each of these pins is connected. This display library comes with a set of core functions. These include display initialization, sending commands, and writing data to the screen. Additionally, it contains specific functions intended for use with the LVGL graphics library, such as display flush, set address window, and others. These LVGL-related functions are essential for allowing smooth and efficient integration of the display with LVGL's rendering pipeline. We will test the LVGL integration a little later in this video. But for now, let's focus on verifying the basic functionality of the GC9A01 display. Start by including the GC9A01.h header file in your main.c file. Now, within the main function, call the GC9A01_init function. This will initialize the display and prepare it for use. To verify that everything is working properly, we'll perform a simple test by filling the screen with different colors. Use the fill rectangle function inside the main while loop. This function allows us to fill a specific rectangular area on the display with a solid color. The parameters of this function include the X and Y coordinates for the starting point of the rectangle, the width and height of the rectangle, and a 16-bit color code representing the color you want to fill it with. Let's begin by filling the screen with a solid red color. After that, we'll insert a delay of 1 second to make the transition visible. We'll then repeat the same procedure for several other colors. Here, I've defined a set of 4 different colors that will cycle through the screen, switching every 1 second. This creates a simple but effective demonstration of how the display is working. Let's now build the project to compile the code. There are no compilation errors, so we could go ahead and flash the firmware to the board. As you can see on the screen, the display is switching between colors every second, just as we programmed it. The colors are also rendering accurately, according to our specified configurations. This confirms that the GC9A01 display is initializing properly, and we are successfully able to draw colored rectangles on the screen. This basic test verifies that the hardware interface, as well as the library, are functioning as expected. Now, we will move forward and add LVGL, the light and versatile graphics library, to our current project. I have already created a complete video series that explains the LVGL library in detail. If you're new to it or want a better understanding, you can check out that series by clicking the link in the top right corner of this video. For this project, we'll be using LVGL version 9.2, which is the latest version currently supported by Squareline Studio. Start by downloading the LVGL 9.2 package in zip format from the official repository. Once the download is complete, go ahead and extract the contents of the zip file. After extracting the files, rename the top-level folder as LVGL to keep things clean and consistent. Next, we need to integrate this library into our STM32 project. To do that, go into your project structure and create a new folder inside the drivers directory. I am naming this newly created folder LVGL to clearly indicate that it contains the graphics library. Now copy the entire downloaded LVGL folder into this new drivers/LVGL directory. Once that's done, the first step in the setup process is to copy the LVGL configuration template file into the appropriate location, right beside the LVGL folder, not inside it. It's important to place the configuration file at the same directory level as the LVGL source folder so that it can be easily included in your project build. Now, rename the template file from its default name to lvnf.h, which stands for LVGL configuration header. Next, open the configuration file in your IDE. To activate the configuration content, locate the macro that disables the file content and set it to 1 to enable everything. For now, I'm leaving all the configuration settings at their default values, since they are suitable for this basic implementation. Let's try building the project once to check for any initial errors. As expected, we're seeing multiple errors, and that's because the LVGL library path hasn't been added to the project settings yet. To fix this, open the project settings by right-clicking the project and navigating to C/C++ build settings. Under the compiler section, go to the Include Paths tab. Click the Add button to add a new include path relative to the project workspace. Now browse to the main LVGL folder that we manually added earlier. Make sure not to select any LVGL subfolders. We need to add the path to the top-level folder that we created ourselves. Click OK, and then Apply and close the configuration settings. Now rebuild the project again. You'll see that all the previous errors are now resolved, and we're ready to move on to the next step. The next task is to connect the display driver with the LVGL library. To do this, we'll use a display porting file, which is already included in the LVGL library package. Navigate to the path, LVGL examples porting. Here you'll find 2 files named LV Port Display Template C and LV Port Display Template.h. Let's copy the .c file to the project's src directory and the .h file to the inc directory. Once copied, rename both files by removing the word template from their names. Open the source file first, and again, look for the macro that disables the file's content. Set it to 1 to enable the code inside. Also, make sure to correct the include path at the top of the file so it properly includes the header. Alright, before we go further, we need to define the resolution of our display. This should be done inside the display port header file. Since the GC9A01 display has a resolution of 240 by 240 pixels, set the appropriate width and height definitions accordingly. Now rebuild the project again. You'll notice that the earlier warning related to resolution has now disappeared. Next, we need to initialize the display. The initialization function for the GC9A01 display is already written in the display's header file, so we just need to include that header here. Within the function displaying it, go ahead and call the function GC9A01_init to initialize the display hardware. After initialization, we'll configure the flush function. The flush function is used by LVGL to send color data to the display memory. As I mentioned earlier, our library already provides a GC9A01_flush function that is designed specifically for this purpose. The parameters of the flush function include the pixel color data, referred to as px_map, and the display area defined by x1, y1, x2, and y2, which indicate the rectangular region to be updated. If you look at the implementation of GC9A01_flush, you'll see that it first sets the address window on the display and then transfers the pixel data over SPI, either using normal blocking mode or DMA, depending on the configuration. After the transfer is complete, the function calls flushReady. This flushReady function is defined as a weak function, which means it can be redefined elsewhere in your project. Let's define our custom version of flushReady inside the display port source file. Within this function, call LVDisplayFlushReady to inform LVGL that the flushing operation has completed and it is now ready to send the next frame. So here's the flow. LVGL calls the flush function. The flush function transmits the color data. Once transmission completes, it calls flushReady, and flushReady tells LVGL it can start the next flush. If you're using DMA, the GC9A01_flush function sends the pixel data via the DMA peripheral. Once the DMA transfer is complete, an interrupt is triggered and the transmit complete callback function is invoked. Inside this callback, flushReady is called to wrap up the flushing cycle. Now open the function LVPortDisplayInit. Inside this function, you'll find different buffering strategies available for rendering frames to the display. If you're using DMA, it is recommended to use 2 buffers for partial rendering to reduce tearing and increase performance. I have explained these rendering techniques in more detail in the LVGL introduction video, so be sure to watch that if you're interested in how buffering works. By default, the library is set up to render 10 lines at a time, but this value can be adjusted depending on how much RAM your microcontroller has available. Let's now build the project again to check for any remaining issues. We're seeing an error in the LVDisplayFlushReady function call. This error is due to the fact that the display object being passed to this function was declared within the flush function's local scope, and therefore isn't accessible from the flushReady function. To resolve this, we need to declare a global display pointer. I'm calling this pointer myDisplay. Once the display is created during initialization, assign it to this global variable. We will then use this globally defined display pointer in our call to LVDisplayFlushReady. Now, rebuild the project once again. The error is gone, and the project builds successfully. Next, open the main.c file. At this point, we no longer need to call the GC9A01 specific test functions. Instead, include the display port header file that we just configured. Inside the main function, begin by calling LV_init to initialize the LVGL core library. Then call LVPortDisplayInit to initialize and register the display driver with LVGL. Inside the main, while loop, make sure to call LVTimerHandler every 5 milliseconds. This is required for LVGL to process events and handle animations. Now, open the interrupt source file, typically named STM32 interrupt.c. Here, include the LVGL header file, which is located inside the LVGL directory that we added earlier. Scroll down to the sysTick handler function. Inside it, call LVTickInc1. This function increments LVGL's internal tick counter by 1 millisecond on each system tick. This setup is essential to keep the LVGL timers running accurately in real time. With this, our LVGL integration is complete. We're now ready to move on and start designing and displaying UI elements on the screen. As you can see here, the basic implementation of LVGL in this project is occupying around 357 kilobytes of flash memory. It's important to ensure that you're using a microcontroller with sufficient flash memory to support this usage. Although you can reduce the size slightly by tweaking the LVGL configuration file, even a minimal LVGL setup still requires a decent amount of flash to handle graphic rendering on the display. Now that we have the basic setup ready, let's go ahead and try out some example animations from the LVGL library itself. Navigate to the folder path, LVGL Examples Animation. From here, I'm going to use one of the built-in examples named animation_2. The first step is to include the header file associated with this example into our main.c file. This header file can be found inside the same examples/animation folder of the LVGL library. Once included, and after the LVGL display port has been initialized, go ahead and call the animation_2 example function to trigger the animation. That's all the setup needed for now. Let's build the project to check whether everything compiles without any issues. The project builds successfully. There are no errors. So let's proceed to flash the firmware to the board. Now, on the display, you'll notice that the ball animation is running. The motion is very smooth, indicating that the display refresh and data transfer are working well. However, there's a slight issue. The color of the ball should be red, but here it appears to be different. If you refer to the official LVGL documentation and look up this particular animation example, you'll find that the ball is indeed supposed to be red in color. This kind of color mismatch is common when using SPI-based displays, and it's typically due to how color bytes are arranged and sent. Earlier versions of LVGL used to include a flag in the configuration file that allowed easy color format swapping, but this flag has been removed in newer versions. So, we'll correct this manually using a software approach. Open the file named lvportdisplay.c, which is the source file for the LVGL display port. Inside the display flush function, insert a call to the function lvColorSwap 565. This function is used to swap the color bytes correctly for RGB 565 format. Pass the pixel data buffer to this function as the first parameter. For the second parameter, pass the size of the buffer, which is simply the area of the rectangle being updated on the display. Make sure this function is called before the flushing process starts, so that the data is already in the correct format when sent. Now rebuild the project and flash it again to the development board. This time, you'll see that the ball is rendered in red and the animation is still running smoothly. So now we have a fully functional LVGL implementation on our display, with proper color correction for the SPI interface. With that confirmed, let's move to the final section of this video, where we will design a graphical UI using SquareLine Studio. Launch the SquareLine Studio application. Click on the Create section, and under Project Type, choose Eclipse with SDL for PC. I'll be selecting LVGL version 9.2, which is the latest version currently supported. That's the reason we downloaded LVGL 9.2 earlier in the setup. On the right-hand side of the screen, provide a location for the project folder. Now set the display resolution to 240 by 240 pixels, which matches our GC9A01 display. The display shape should be set to circular, and the color depth must be 16 bits, corresponding to RGB 565. Make sure to select the correct LVGL version, which matches the one already integrated in the STM32 project. Click Create to generate the new UI project. Now you'll see the circular screen preview for the new design. Let's begin designing by adding an image element to the screen. I've already prepared an image in PNG format, resized to exactly 240 by 240 pixels. We'll import this image into the Assets section of Squareline Studio. Now under the Image widget, choose the image we just added to the assets. Next, I'll also add a spinner widget, which creates an animated arc, useful for visually indicating activity or loading. Go to the main style settings and adjust the arc width to suit the design. Then adjust the indicator style settings for the spinner to match your preferences. Try experimenting with different colors for the arc until you find one that looks good. Once you're satisfied with the design, open the project settings. Here, we need to define a folder path to which the UI files will be exported. Inside the main project folder, create a new folder and name it UI. Now set this folder as the export path for the generated UI files. The LVGL include path in our project is located inside another folder called LVGL, so include the path accordingly. Click Apply Changes to save the export configuration. Now click on Export to generate the UI files based on the design. Once the export is complete, open the project folder and navigate to the UI directory. You'll see all the UI source and header files generated by Squareline Studio. Copy this entire UI folder and place it inside the LVGL folder that we added to our STM32 project earlier. This keeps all the LVGL-related files grouped together for better maintainability. Now go back to main.c. To use the new UI in your project, include the header file ui.h, which is located in the UI folder. After initializing the LVGL display driver using LV port display init, call the function UI_init to initialize and load the UI onto the screen. Let's build the project to make sure everything compiles correctly. The project builds without any errors, so go ahead and flash it to the board. On the display, you should now see the image and animated spinner loaded and running. The animation is working very smoothly, confirming that both the display and the LVGL integration are functioning properly. We now have a complete setup where the GC9A01 display works with LVGL graphics, and the UI is generated from Squareline Studio. That brings us to the end of this video. I hope you now have a clear understanding of how to interface the GC9A01 round display with STM32, how to implement the LVGL graphics library, and how to design and export UI using Squareline Studio. In the next video, we will continue working with this display and create a custom analog watch face. We'll be using the real-time clock peripheral to display the current time on the screen. You can download the complete project files from the link provided in the video description. If you have any questions or run into issues, feel free to leave a comment below. And if you found this video helpful or informative, consider giving a thumbs up. Thanks for watching, and have a great day ahead.